Okay, we have a little bit of confusion about Coulomb's law, so let's make sure we understand. Coulomb's law says that the vector force of one charge on another is this. For R is the vector from one charge to the other, and you got to keep that straight. So I'm not going to talk about that. You know, it'll come up. But this is the unit vector. This is well, what I said a minute ago is quite true. Magnitude of this thing is the magnitude of the force. This thing could be positive or negative depending on whether Q1 and Q2 have the same sign or opposite signs. So if you have two positive charges, Q1, Q2 is of course going to be positive. If you have a positive and a negative, then Q1, Q2 is going to be negative. If you have two negatives, well, you multiply two negatives, you get a positive. So if unlike, one's positive, one's negative, whichever one. Okay. Either Q1's negative, Q2's positive, or Q1's positive and Q2's negative. I think I said that right. There are four possibilities for the signs of Q1 and Q2. Two of those possibilities, the signs are opposite. So you have a positive force. A positive, this is a positive quantity. And in two cases, the signs are opposite. You have negative quantity. And again, I think I said that right. Okay. So this is the magnitude of the force. I'm saying this is the magnitude of the force. If Q1, Q2 is positive, meaning they have the same sign, so that's the force of repulsion. So that this vector goes from one charge to the other. And if the force of repulsion, that's the direction of the force. But it could be a force of attraction. R still goes from one charge to the other. But now the force is in this direction. Okay. Now, to get a force in this direction, you would multiply the unit vector, which is in the direction of the force, by a positive number. You multiply the unit vector by a negative number, it's going to give you a force in the opposite direction, which would be your force of attraction. So you have to understand all that when you see this, okay? And it's a magnitude of Q1, Q2 positive. It's a negative magnitude if Q1, Q2 is negative. So when you multiply by the unit vector, okay, so you got charge okay. This would be your vector R12. Okay. Unit vector. And let me just color code this. Unit vector is R12 over R12. So let's say this is your unit vector. And then if both charges have the same sign, it's a force of repulsion. You multiply the magnitude by the unit vector, right? If it's a force of attraction, and I'm not going to try to draw that, but if it's a force of attraction, that means Q1 and Q2 have opposite signs. So when you multiply positive and a negative, or negative and a positive, you get a negative. And you multiply that unit vector by the negative of the magnitude, making it a force of attraction. Now we did this with gravitation. There was always a force of attraction, so you always had the negative there. Okay. Again, you really kind of want to go back and see. A negative sign on it because it's gravity only is an attractive force. Okay. In that case, this is the magnitude of the force. But you've got to reverse it. You've got to multiply it by the negative of the unit vector, basically, which gives you a negative sign. Okay. And I totally have to understand that in terms of, you know, what you understand about vector calculus and everything else. And you know, this camera, I love it and I hate it. Does a really good job, but it changes its zoom and sometimes it goes out of focus. I can control the focus by not walking in front of it. I don't know why I'd want to focus on me instead of a board. The board's important. There it is. Okay, so good question. Make sure you understand that. Okay. X-axis, y-axis. Charge distributed along the x-axis. I got positives there, but it could be negative charge because I'm going to do this in symbols anyway. What I'm doing doesn't depend on the sign of the charge. But it's a uniform charge density, okay? Or charge per unit length. You can also do this with a disk of charge. We have a charge per unit area, and we will. Very important stuff. Okay, you got a charge per unit length of lambda though. Okay, so now we want to find net force and a charge Q at 0A. What do you think you're going to do? You're going to subdivide the entire x-axis. You're going to partition it. Start by partitioning the x-axis. We've done a huge amount of this in physics and especially in multivariable calculus. So this should be getting really familiar to you. It's a push, but we've done a whole lot of it. But if you didn't do it in first year calculus, it's an even bigger push. Needs to be done. COVID year doesn't always get done, okay? You understand why, but you have to get this. Partition the x-axis in typical interval. Now let me just kind of put you on the spot for a minute. Turn off the camera. Okay, your typical delta x interval. Well, you can do it this way, right? Main thing is, I didn't really drag this out of here, but length delta x There's a little bit of funny stuff about the closed or open intervals. Okay. And when you put a bunch of half open intervals together, you don't get one or the other endpoint, and it gets confusing. But since what happens at an individual point doesn't make any difference, it doesn't really matter. So you kind of forget about that. Okay, we're going to say length delta xi. And the thing I was trying to get at, of course, then is the sample point. And you can help with that. So what you said was xi star. Okay. What you really want to think is sample point, so let's call it xi star. Because then you understand it's a sample point, which means you understand what you do with it, but I think you do anyway. Okay. So I'm not being picky on this one. A little insight into how you might want to think about it. Okay. So you got a sample point xi star. So I can put this interval anywhere, right? So let's put it over here. I could label xi minus 1 and xi, but we kind of understand that. We got a delta xi here, and we got a sample point. Xi star. No. We want to use coulombs law. We want to use this expression, right? Okay. So what are we going to use for Q1 and Q2? Well, we set a charge capital Q at 0A, right? And we want the force on this charge. So we'll just go ahead and call this. No good place to label it. Charge Q, right? Now, what charge do we want to use for Q1? So we're going to call that our Q2, right? What are we going to use for Q1? Now, we'll say it took us a little too long to get to this, but the question was, how much charge is there? So how are we going to calculate the force due to this interval on this charge, right? So we know that we have to have two charges in an R vector, right? Okay, so you got the R vector quickly, and that's good. That's one of the hurdles, right? So you're pretty good there. One is equally good on identifying how you figure the other charge. So a force on Q due to the ith interval. And you pretty well got this. And you said this very quickly. Your R vector is from based on xi star. Based with a D on the end. Okay. Based on xi star. The interval, that's incomprehensible, so I can pretend I wrote it right. Assume the charge in the interval is concentrated. The point xi star 0, because that's what you do. You calculate everything based on the sample point and whatever quantity of stuff you have in the interval. Okay, charge in the interval concentrated at xi star at 0. The charge in the interval, as I say, because it took us a while to get this. People want to divide the length of the interval by lambda and do all kinds of things, right? We demonstrated that the units just don't work out. It's not dimensionally consistent to do that. You want to get a charge. You don't want to get meters squared per unit of charge, length squared per charge, right? You want to get charge. So you could reason it out by units, or you could reason it out by having an intuition about what a density is. Now, you've done a lot with density, especially multivariable calculus. Okay, so you really want to lock in the concept of density at this point, because charge density is extremely important, even more important in this context than mass density. Okay, and you should know what to do with mass density because you've done all kinds of mass and moment intervals and so forth. Okay, well, and that all goes back to calculus 1, no, calculus 2. More than calculus 1, where you would have done your first density intervals. Okay, and if that didn't happen, it's probably due to COVID. You know, that sacrifices were made. So you got to make that up. Okay, so make sure you do. Okay, the charge in the interval is, and it should be obvious, lambda times delta outside. Your density and charge per unit length by your length. Okay. Okay, well, now can you write down for me the expression for the force? Okay, say start with your R vector, that should be easy. If you use the fact that you have 2 points, if you're going from this point to this point, you subtract where you start from where you finish. That's something you always do, and you always want to understand that. I go from milepost 17 to milepost 30, then I've got a plus 13, which is what you get if you do 30 minus 17, right? If I go from 30 to 17, then I've got to do 17 minus 30. I always subtract where I start from where I end. Okay, and this is your vector. I'm just writing it in order pair right now. The temptation would be when you look at this that, oh, there's the distance is delta xi. Well, from here to here is not delta xi. I'm sorry. Your distance from here to here is xi star. From xi star to 0, but that's not right. Okay. Displacement is negative xi star because xi star here, the way I pictured it, is negative. Now, if I'd have pictured over here as positive, then I'd have had to do back up. Okay. This displacement is positive, right? And xi star is negative, so the distance is not xi star. Distance is negative xi star, which is a positive distance, right? Positive displacement. If I'd have started at a positive displacement, then my displacement in the x direction would have been negative. My x would have been negative, and if xi star was positive, then negative xi star would, times I would be a negative displacement. So you got to sort that out because it's a really common source of error, not just in physics, not just in calculus, everywhere. Okay, you have to keep these things straight, and you got to be very careful with them because it's really easy to get them wrong. It's closely related to the most common errors computer science, computer programmers make. Okay, and computer scientists, everybody, you got to be careful about signs. Okay, make sure they make sense. Now, what are you going to use for your two charges? So now we have, written really badly, but down too low. Q1 equals lambda delta xi. That's, here's Q1, here's Q2. Our vector is going from here to here because we want the charge on this charge capital Q. Okay. So Q2 is your capital Q, and Q1 is a charge in this interval, which is lambda delta xi. I'll write the force at delta F sub I. It's going to be K. Q1, which is lambda delta xi, Q2, which is Q, over R squared. Okay, well, what's R squared? The square root of xi star squared plus a squared, right? So R, well, that's R squared is, R is the square root of the sum of the squares by Pythagorean theorem. We want R squared, so we don't even have to worry about a square root. If xi star plus a squared plus a squared, and that's multiplied. I didn't leave myself room, so I've got to spill over here to your R vector over its magnitude. So then we are going to get a square root, and that's going to give me okay. Well, there it is. It's a perfectly good vector. And of course, we can now write it as K times lambda Q over three halves power of xi star squared plus a squared. Times xi star I, negative xi star I, plus aj. I was going to write my delta xi out at the end, but I don't have room. Okay. So the sum of your delta Fi is what? First of all, you got K lambda Q out in front. You can all be factored out. Then it's the sum over I I'm not going to write I equals 1 to n or anything, but just get the idea. Sum over I, review your calculus, see how to write it out in detail. And when you get tied up in those details, I want the concept. The concept is we're getting the force for one interval. Now we're going to sum it up for all intervals. Whether this is an infinite line or a finite line. Okay? We partition whatever the interval of the x-axis is, and we get the result. So we sum over I of correct symbol xi star I plus a over xi star squared plus a squared and 3 halves times delta xi. Then if you understand approach to the limit, your delta xi becomes a dx. Your xi stars become x's, and now we have an integral. Okay. Now, if this is the infinite line, then the integral will go from negative infinity to infinity. Okay. And your negative, and it's not xi, it's just an x. No, it's x times the I vector. I had an arrow over it before. I don't think I did. I think I wrote it as a subscript, which is really careless. Okay. The integral of x over this quantity, or the integral of negative x, it wouldn't matter, because the integral on one side is going to be equal and opposite to the integral on the other side of the origin. So this part of the integral is going to be 0. Okay, because on one side you're integrating positive x's, and the other side you're integrating negative x's, right? And these quantities are always the same. Everything balances, and there's a geometric reason for that we'll see in a minute. Leave myself room, so I have to write my J here. Meaning that your force here, if you accept the fact of the anti-symmetry, the even odd nature of x over the square root of x squared, or the 3 halves power of x squared plus a squared. Okay, just by the symmetry, that integral has to be 0. It's got to be the negative on one side of what it is, and the other side that goes back to even odd functions, which you learned early pre-calculus, which you really need to understand in this context. So kind of make yourself a note. Anyhow, so what happens here? Well, why do the xi stuff go away? It's because for every interval over here, you could have an interval the same distance on this side, okay? And the x component be in one direction here and the opposite direction here, so that your x components, and I kind of say, okay, let's just say we've got an interval here on the opposite side, and this will be negative x on x plus. This will be a delta x same length as this one. Then the force that you get as a result of this R vector would be like this. Well, that's supposed to be blue. Well, it's blue green. Okay. And the force that you get from here would be like this. And the x components will be equal and opposite. For any interval over here, you have an interval over here that gives you the equal and opposite x components with only the y components that add. And that's exactly what comes out of the integral when you consider that the integral of x over 3/2 power of x squared plus a squared is going to give you 0 over the entire x-axis, or over any interval of the x-axis that's symmetric with respect to the origin. Okay. Now that integral can be worked out, but I'm going to let you read because we've spent way too much time on this, but this is an important process. And it's important to understand this symmetry and how the symmetry is related to your integral. And of course, at a lower level, it's important to understand how to get this integral. Just using what you pretty much knew how to do. Okay, take a typical interval and see what happens in that interval. And everything else assembles into your interval. You need to think about this process. We can do the same thing for a circular ring of charge of radius, say alpha. And I would parameterize this as follows. Partition the interval 0 to pi. Typical increment theta, I minus 1 theta, I length theta. Sample point theta, I star. So what can you tell me about the force corresponding to your typical theta increment? The force on this charge. What does the theta increment tell you about the interval on your ring? I'll just say that here's a theta interval. And a sample point. By the theta interval, I mean all this. Okay. And I really should probably use the word increment. So my question is, what's your length interval? What's your sample point on the ring? And what force is exerted on a charge capital Q on this z-axis. Okay, so the first answer I got to the point on the ring is sine theta sub I star cosine theta sub I star. It's not bad, but we want to make sure it's correct. In the first place, sine theta sub I star cosine theta sub I star is a point on the unit circle. Okay, this isn't a unit circle, it's a circle of radius alpha. Okay, so you would want to multiply that by alpha, and you'd be a lot closer. You'd almost be there, except that the cosine is your x coordinate, the sine gives you your y coordinate. Okay, so you know your x coordinate. I didn't leave myself room to label it, but I can draw a little circle out here. If my radius is alpha, well, if this is a unit circle, I'm drawing this pretty small because I don't want to use up too much room. Then this coordinate is cosine theta, and this coordinate is sine theta, and that's your definition of the sine and the cosine. So that's something you've always got to carry with you. Your circular definition of your two basic trigonometric functions, and all the other functions come out as ratios of those. You know, of course, you got an r here, so you got r cosine theta and r sine theta if you want a circle of radius r. Okay. Obviously, if this is on the unit circle, then on the circle of radius 10, you'd have 10 times the coordinates, 10 cosine, 10 sine. Okay. If it's on radius a, it's alpha times the cosine, alpha times the sine. So we need to reverse the coordinates, but yeah, just the fact that you came up with that is a good start. You did leave off the theta. You did have your cosine and sine reversed, and you really want to be sure you totally understand the sine and cosine functions at this stage. For your engineering courses as well as your physics and math courses, okay? You want to be sure that's kind of second nature. You don't want to be stumbling over that, okay? But again, your answer is such that you're going to understand this, okay? So there it is. Sample point is this. That applies whatever quadrant you're in, because the sine and cosine will take on the signs of the positive, negative signs of their coordinates, okay? So there's your sample point. Except that now we're in 3 dimensions, right? So we really want to put this in 3 dimensions so we can articulate it with this point. What's your RI vector? The vector from this point to this point. So you should be able to just write down that vector. Give you a minute, but not much more. So your RI star is what? You subtract where you start, which is here, from where you end, which is here. Okay, well, 0 minus this is negative alpha cosine theta sub I star times your I vector, and then it's minus alpha sine theta sub I star times your j vector plus a times your k vector. Just coordinates at this point minus the coordinates at this point, but we actually regard each of these points as a vector position. So you're subtracting alpha cosine theta sub I plus alpha sine theta sub I j plus 0k from 0I plus 0j plus AK, and you get this vector. Now, okay, your charges are Q up here, which are charged down here. Well, we've got a sample point, so we've got our R vector, we don't have our interval yet. How long is our interval here? So our limits on theta give us an increment here, right? Okay, so there's kind of a picture. Here's our theta interval, and here's our actual interval on this ring. So how much charge is there on the ring corresponding to the theta interval? Okay, so there are your charges are Q and lambda times the length of the interval, whatever length that interval is. Length of the interval, alpha delta theta sub I. Definition of radian. Back when we were converting between linear motion and rotational motion. Okay. We used it again and again for the formulas that connect the two, but those formulas are just the definition of a radian, and much more efficient to understand in terms of the definition of a radian than to memorize a bunch of formulas that are confusing because you don't know what's in the numerator and what's in the denominator unless you know the definition of a radian, okay? Or unless you have a photographic memory. Okay, so anyhow, length of the interval is this. So these are two charges. At this point, there goes two charges and your R vector into Coulomb's law, and you've got it. Then, of course, you sum all that up and get an interval. Now, as we talked about last time, for this particular interval here, we get a force like so. There's an interval in on the opposite side of the circle with its sample point. Gives us this and gives us this. Once more, this distance being equal to this distance, if the length of this interval is the same as the length of this interval, you get equal and opposite components in the XY plane. And only the component in along the Z-axis ends up contributing to the total force. And if you just visualize all this thing subdivided into intervals, like you got this TP up on top, okay, with these vectors going every which way, but always canceling out in pairs, always canceling out the X and Y components, the I and J components, for any pair, leaving you just the K component. And you ideally would see that in the integral that results. Okay, at this stage, we pretty well covered the first chapter on Coulomb's law and electric forces. Next thing we do is we talk about the flux of an electric field. And all the electric charges give rise to electric forces, which give an electric field at a given point. The field's just the amount of charge per unit of test charge. Okay, so you understand, we get these vectors. So you get these vectors throughout space, and they can have a flux through a surface. We're going to look particularly at a flux through a spherical surface, a cylindrical surface, and a plane. Okay, fairly simple flux calculations. You're not going to have to use your multivariable calculus. Okay, because we can in these situations, you understand that all your multivariable calculus becomes important at some point, but not in this course, except for the insight into what flux is, the amount of charge you have going through a surface. Okay. And then we use the divergence theorem, which is Gauss's law, to simplify the calculations of electric fields in certain important configurations. Okay, like we do the field of this line charge here using Gauss's law, and we don't have to do all this developing the integral. We don't even need an integral. Okay. This is a little trickier. We wouldn't probably do that, but if you have charge distributed over the whole x-axis, that whole xy plane, then we can use Gauss's law to, again, not have to worry about the details of the integral. Okay, so it's a big time saver. It's conceptually important, and you get a chance, just read a little bit of the section. Just leaf through, scan the next chapter, because that's what we're going to be into next time. Okay.